Okay, welcome everyone, and thanks for coming. And I want to let you know the plan today. As always, I'll answer any questions you might have, and that could be, throughout the whole time. But I always like to start with questions if you have any. And then after that, really, we're moving to the next half of the class. We're really going to, there's really two parts of the class. And starting today, everything we do is about applying. We're using statistics. We're taking data and we're looking at the data and using that to get inferences about the population. That's really what this is. So normally your population is gigantic, like all Americans. There's just no way in the world you can ask them all or find out exactly what they are. You take a sample, and then if you do it, if you take a good sample with unbiased sampling methods, then you can say, all right, I got my sample. So how good a predictor is a sample for the population? That's really what we're doing for the entire rest of this course, is we're using the sample to predict the population. So this week, it's all about what's called confidence intervals. So confidence intervals are saying, well, I have my sample, and let's say you sampled and you found out, I don't know, if you found out the average age of the pet dog was 5 years old, because you surveyed, 100 people who had dogs. But the problem is there's, millions and millions and millions of dogs in America. And is that 100 a good estimate for the entire population of dogs? And how good is it? How much off might you be? That's kind of what this is all about. And we're going to have what's called a confidence interval for a mean. So you have your sample, and this is for when the survey question is quantitative. So that means that you can talk about a mean or an average. And the question is, you have your average for the sample. So how close is that to the population? How close is it likely to be to the population? And that'll be called the confidence interval for the mean, is to say, well, it's going to be in this range somewhere. I'm pretty confident that the population mean will be in this range. And that's what today is all about. And then we're just going to move on to proportions. So same idea, but instead of a quantitative survey question, it'll be a yes/no survey question. So, instead of how old is your dog, it might be, do you have a dog? And then you might say, well, what percentage of all Americans have a dog? And nobody knows, by the way, exactly what percent, because you'd have to ask everyone, and you can't do that. But what you can do is you can do a survey and then say, based on survey, I have a pretty good guess. This is what my best guess is, but I might be off by a little bit. Well, how much off do you think you might be by? At most, what amount? And that's called a confidence interval. And in this case, it would be for a percent or a proportion. Then once we go over that, we're going to get into something that is very important. And it's easy to just kind of not think about. But if you don't think about it, you can end up with a disastrous result. And that is sample size. So if you're going to do a survey, how many people do you need to survey? Do you need to survey 1 million people? Okay, which isn't even close to the number of Americans, for example. Okay, maybe surveying 200 people is good enough. And you certainly don't want to waste your time and survey 1 million if 200 was good enough. Okay. On the other hand, maybe 200 is not good enough, and then you've wasted your time. You'd have to survey meaningless. So we'll talk about how big a sample size you need for it to be a good predictor. And I'll get into the details of what a good predictor is. And just like 2 and 3 on the list, 4 and 5 will be sample size for means, and sample size for proportions. So it's a different formula, whether if you're doing means versus you're doing proportions. And we've kind of seen that already, that means and proportions are really two pieces. Okay. So that is the plan for today. It's not too bad. One thing is that this is the week 6 webinar. What's important about the number 6?
We have a quiz this week.
Yeah, I call it an exam. You can call it a quiz if you want. Yeah, it's an even 6 is an even number, and even number weeks is when the exams happen. Okay, so don't forget to take, to get ready for that exam. And I want to remind you, it's always going to be the same when I talk about with the exams, is that the exams cover everything that we've done since the beginning of class, but they're weighted more heavily on the last 2 weeks, week 5 and week 6. So there'll be more questions and more points on chapters 6 and 7, but there's still going to be points on chapters 1, 2, 3, 4, and 5. And that's how it's going to go. And this will be the 3rd time you've taken an exam. So you should know what's coming at you. Yeah, I try to make them all look somewhat similar. The first bunch of questions are literally just randomized questions from your assignments that you've been doing for the last 5 or 6 weeks. And then the last couple questions are where you have to write out full explanations of stuff. And that's where you really have to listen to the webinars, especially, because that's where the explanations happen. They're actually on the assignments, but they don't on the regular assignments, but the assignments don't ask you to write them out. It's more multiple choice. But for the last couple questions, are not multiple choice. You actually have to type them out. So that's just a note. So you do have your week 6 exam. I also want to let you know that this morning, I actually finished grading the last of the projects, project 1. And so you should have, I think you get a notification in Canvas when the grades happen. But if not, I'm notifying you now. The grade is there for you. And a couple things. One is the biggest disaster that happened for the projects was not working with a partner. It's you pretty much can't pass if you don't work with a partner. And I warned you about that earlier, because it's an automatic 25% deduction. So even if you got 85%, you still have a terrible grade. Okay, because that dropped 20%, and now you have a 60%. So not having a partner was a disaster for those that submitted the project without a partner. And there was more than one of you. So I just want to let you know that can't happen. Okay, and I thought I was very clear about it for the last bunch of weeks. So if all the partners withdraw, so the good news for project 2 is you don't have to use the same partners. So you just find new partners.
But I mean, for project 1, what if all their partners withdrew the class and it was just one person left in that group?
Well, then hopefully they found new partners, in the last week or 2.
Because I had somebody message me the day before the project was due and ask if they could join our group.
Mm-hmm. Right, and that's what you do. You join a group.
And can we have 4 partners, or?
No, you can't have 4, but you can split into 2. But to be honest, there were multiple people who turned in their assignments, their projects without a partner. Those people could have formed a partnership. And had they emailed me, I would have helped them out. You know what I mean?
Oh, gotcha. Yeah.
Yeah. So I will make it so anyone who needs to find a partner, we'll do it. You'll find a partner. But you have to do the work to get a partner. Okay. And it's not that much work. It's posting on the project discussion board. And by the way, let me do this now. You go to discussions, since we're at it now. And by the way, this week's a little bit lighter, so I can spend a little more time talking about this. And just a note, where is it? There we go. Let me put it on the pin list. And I'm going to take this one off. There is a project 2 discussion forum. And so that's where you post if you need a partner. Okay, and also later, we're not ready yet, but that's where you post your projects, ideas, and all that. But we still have time before you're ready to even think about project 2, other
And
than making sure you have partners.
if we want to work with the same partners, do we need to post on there?
No, if you want to work with the same partners, the one thing you definitely need to do is contact your partners and make sure they want to work with you too. So that you know you're good. Does that make sense?
Yes.
Yeah, because partners get to decide, everyone gets to decide who they work with, but it has to be both ways. Yeah, so make sure that if you want to work with the same partners, that send your partner a message, however you've been messaging them, and then say, hey, can we work together in project 2? And if they say no, then you post on the project 2 discussion board. If they say yes and you're happy, then you stick with your partners. That makes sense? Yeah. So that's the idea. So it is important. So one thing I can talk about project 2 is that you need to make sure you have partners, because it's a disaster to not have partners. Okay. And it's not just the 25% deduction. When you don't have partners, lots of things go wrong, because then you don't look over each other's work. It's just not the same. And it was kind of obvious. It was kind of obvious from those who submitted by themselves. It's not like they were great, they were great projects, but they just didn't have partners. It was clear that they didn't have a group and they weren't doing the same stuff. That makes sense. Any questions on that? Okay, let me talk about the new stuff. And we're going to have a small sample size. But I have a survey to ask you, and you have to post it in the chat box. I won't say your name or anything. The rule is you have to answer it, but if you don't feel comfortable telling anyone, then just make up a number that's reasonable. And by the way, if you have not experienced your first passionate kiss, then just state your age, and maybe it'll be this year. And maybe I should post just because we get enough. Okay, this turns out to be actually much more important than you would think. Okay, so we have everyone answering. And the question is, how old were you when you experienced your first passionate kiss? And our data was 18, 16, 15, 13. Okay. So we have our data. Now, the question is, what can we do with it? Okay, and this is a very small sample size. And in reality, you would never use a sample size of 4 to do anything statistically, but that's what we've got. So we're going to use it. But I will mention something when we're done. Something I've been doing. I've been asking this question since I started teaching over a quarter century ago. So I've actually seen what's happened in the last 27 years, actually. Okay, so what we can do is, the first thing I can do is I can take these numbers and I can get statistics out of them. I can get my sample statistics. So I can go to the one variable statistics calculator. I can pop in the numbers, copy and paste. This is a sample. I get it calculate, and this will give me my sample mean, 15.5. So let's put that in. It'll give me my sample standard deviation, which is about 2.08, good enough. It will give me my n, which I already know, that's 4. How do I get the standard error, by the way? Who remembers? Gee, there was a nice thing about n equals 4. How do I get the standard error? This is very important. It happened last week. That's a hint. So SE for standard error. You remember? Not seeing y'all jump in. All right, maybe I'll remind you. Okay, so the standard error, that was the standard deviation of the sampling distribution with the sample size n equals 4. And the central limit theorem told us that the formula for the standard error is sigma over root n. In this case, we have s, so we'll do s over root n. So let's go and put that in. And that's 2.08 divided by, shift these, I have to do it this way. 2.08 divided by the square root of 4. And you're never required to do what I'm about to do, but I can do this in my head and I get 1.04. Okay, usually won't be the case. You won't be able to do it in your head, but this one's not hard. You can use a calculator if you want. Okay, and that's my standard error, which remember, it was a standard deviation of the sampling distribution. Any questions on that? Okay, what it does is it gives us an idea of how off we might be from the population mean using 15.5 as the sample mean. Okay, because remember, it's a standard deviation. Standard deviation gives you how far apart the data tends to be from each other. And we're going to assume we have a normal distribution, which means that it's likely that we're no more than a year, 1.04 is about a year, off in our guess of 15.5. Any questions on that so far? Okay, that makes sense? All right, so that's a big deal. So this stuff, this is a review of what we've already done. But what we can now do is we can do a little bit more. And again, we're going to assume we have a normal distribution. Why do I have to assume that we have a normal distribution instead of just know we have a normal distribution for the sampling distribution? Here's a hint. Why do I have to assume that we have a normal distribution? It's not about even and odd numbers. Something about the number, but it's not about even. Remember? Central limit theorem. All right, if I don't see it, because our sample size is 4. Remember that if you have a sample size over 30, that was the central limit theorem, then you know you have normal distribution. You don't have to assume it for the sampling distribution. But our sample size is too small. It's just 4. If it had been, say, 34, then I wouldn't have to assume we have a normal distribution because I would know we have one. Any questions on that idea so far? Okay, but I'm going to assume we have a normal distribution. And by doing that, I can draw a picture. So here's a picture, and it's a normal distribution picture. We're going to say X bar is kind of our mean because that's our best guess. It's our best guess. And we learned from last week that the sample mean is an unbiased estimator for the population mean, which means that from our data we have, this is our best guess for the population mean. So we're going to pop that in the middle. Okay, then what we're going to do is we're going to say, let's say how far from X bar might you need to go so that you're pretty confident that the population mean is within that interval. Any questions on that? Now, do you remember we had a definition of what it means to be an outlier? Do you remember what that definition was? Anyone recall? So we talked about when do you have an outlier? An outlier means very rare for that to happen. So it's very likely that any number you pick is not going to be an outlier. Doesn't mean it can't happen, but that's what outliers are all about, is they're the rare ones. Remember, I don't see it. Remember, the z-score needed to be less than 2 or greater than -2. Those are the key numbers. Or another way of saying it, yeah, it goes far outside the average value, but in particular, it goes 2 standard deviations outside. So it's a very specific farness outside. Do you remember that? And it was 2 standard deviations outside. So the kind of the typical way to do this is you say, well, what is 2 standard deviations? Well, 1 standard deviation is 1.04. So 2 standard deviations for the sampling distribution will be twice that, or 2.08. Any questions on that? So if I go left and right by 2.08, then if you remember, the empirical rule says that if you go 2 standard deviations to either side, that is going to keep 95% of the data within. So that means that we can be 95% confident that the population mean will be within 2 standard deviations of the sample mean. Any questions at all on that big deal right there? Any questions? This is very important. All right. So what we can do is we can find the 95% confidence interval. So what we're going to do is we're going to take the 15.5 let me put a bracket actually, 15.5, and we're going to subtract 2 standard deviations or 2 standard errors, 2 times 1.04. And we're also going to take 15.5, and we're going to add 2 standard deviations. Any questions on this idea? Okay, and that will be our 95% confidence interval for the population mean age of first kiss. Okay, and I could do this calculation. Could use a calculator, but I can probably do this in my head, because 2 times 1.04. Why am I using 1.04? Because it's a standard error. And what we're looking at is we're saying, how far do you think the population mean might be? And remember that the standard deviation of the sampling distribution gives you an idea of how far your sample mean is from the population mean. Whereas the standard deviation of the just population gives an idea of how far a specific number is from the population mean. But we don't have just a data value. We have X bar. So if you want to find out how likely it is that X bar will be from the population mean, then the standard error is what you use. If you want to find out how likely it'll be that one particular person's age of first kiss will be from the population mean, that would be the standard deviation. Does that make sense? And for confidence intervals, we always use a sample mean. And that was chapter 7 stuff. Yeah. So the central limit theorem. Okay, so now I can, again, you don't have to do it in your head, but 2 times 1.04 is 2.08. 15.5 minus 2.08 is 12. Whoops, over here, 12.7. And 15.5 plus 2.08 is 18.3. Any questions about this little calculation? Okay, and again, you don't ever have to do it like I did it. You can, calculators are always allowed. In fact, we're going to have a much easier way, which I'll show you in a bit. But I kind of wanted to kind of show you how you use a central limit theorem, what goes on instead of the magical calculator I'm going to show you in a little bit. Okay, so just to note, this is kind of what I just said. I just talked about this, but I want to mention something, that what we did isn't quite perfect. Okay, it's good for giving an idea, but there's an issue. Anyone see the big issue? Why would I do the calculation I did had a problem? It's kind of subtle, so there's a good chance you won't see it. Okay, if I don't see your answer, that's okay. It has to do with the standard error formula. The standard error formula it turns out that it's not S over root n, it's sigma over root n. It's the population standard deviation over the square root of the sample size. The problem is we don't know the population standard deviation. So we use S as an estimate. But when you have an estimate, that means there's going to be an additional error, it turns out. Okay. And this is where I am going to just tell you to trust me, which I'm going to do this a lot in this class from now on, that there is a way of incorporating that additional error into the that confidence interval so that we really get the right answer. Okay. And it turns out the funny thing is it has everything to do with beer. I'm sure you wouldn't guess that, right? And I'm sure you have no idea what has anything to do with beer. It had to do with the fact that the guy who figured out that there was a problem in using Essence for this, and that there was this problem with, just doing what I just did. He was actually he was teaching statistics, and he was also working for a beer company. And he was realizing that he wasn't really getting it right 95% of the time, and that's what he was hoping for. So he came up with some pretty hardcore math, which I'm not going to show you in this class, to deal with that. Okay. And instead of the normal distribution, he actually named the distribution that the mathematics that he came up with after his students. And he called it the student's t-distribution. So it turns out you're going to use the student's t-distribution instead of the normal distribution. And that's what we're going to be using. So you're not going to it turns out you don't get a z, you get a t. And that's because of this not knowing the population standard deviation. Okay. How it works, I'm never going to tell you in this class. And if you came to my office, I wouldn't have time to tell you. It would take like weeks. Even if you knew calculus, it's really hard. So even Kyle, I can't explain it to you. Just let you know that. I know it, but that's because I took it in graduate school. But let you know that we're going to use the student's t-distribution to come up with it. So let's do that. And I'm going to show you the better way of doing it instead of the way I just did it, which was understanding how this stuff works. But then there's a subtle t-distribution thing that is too difficult. So I'm going to go back to the calculator menu. And now I'm going to go to a confidence interval for a mean with data. Notice I have data because I have my 4 data points. Okay, I have statistics, but data is easy enough, and usually you have data. So I want to show you this one. So what I do is I put my data in, and I have to put my confidence level in, and it does let you know, write it as a decimal. So for example, 95% confidence level, enter 0.95, don't enter 95. So 0.95, and I hit calculate. Any questions on that? Okay, by the way, here's the 15.5 and the 2.08 that we already knew. Just gave it because when I programmed this, I figured some people want to know these things. But then it also gives you the lower bound and the upper bound, which is about 12.2 to 18.8. Any questions on what I just did? Okay, I tried to make the calculator easy. You just type in your stuff and hit calculate. So 12.2 to 18.8. Any questions on this at all? Okay, next is we want to interpret what this interval is. Okay, we have these numbers, a lower bound of 12.2, an upper bound of 18.8. So we want to interpret this. And here's how I'm going to interpret it. And this is what we write: with 95% confidence, the population mean age of first kiss is between, and I guess I should say first passionate kiss, because we were all kissed by our parents when we were an infant, but that's not passionate, that's different. Okay, the first passionate kiss is between 12.2 years old and 18.8. I'm going to make this a little bigger so you can see it because it's that important. Any questions on this interpretation? So just to help you out, whenever you're asked to interpret this confidence interval, so for example, you're going to have to do that for the discussion post assignment. You're also going to have to do it for your exam that you take at the end of this week. Start with this word right here, with. It'll get you going. Okay, it's an easy word to remember because it's not like some fancy statistics word. So whenever you want to interpret the interval, then you just start with the word with, and that will help you out. And then it's with 95% confidence, the population mean age of first passionate kiss is between 12.2 years old and 18.8 years old. I guess I already did that, so I don't have to do this. Any questions on that? All right, so the next thing is, what does it mean to be 95% confident? So here we said with 95% confidence, but that's kind of vague to say that. I'm confident. Well, most people don't understand what that means to be 95% confident. So let me go over what's going on here. What we did is we have this distribution, this normal distribution. And this X bar and this distribution is all about the sampling distribution. Now, the sampling distribution is a collection of all the different possible sample means. And when you have a 95% confidence interval, that means that there's a 95% probability or 95% of the possible sample means is going to be in this area, in this region. Any questions on that idea? Okay, and I want to give you a little history, very old history, by the way, close to 100 years old, actually. And that is someone had to decide that 95% was the level of the confidence that everyone uses, right? Or not everyone, but the most common. And here's the thing, and see if you know your history. Who made that decision? And the hint is it was the news agency of the time, like 100 years ago. In those days, there weren't a zillion news agencies. There was basically one news agency in the country. Anyone know what it was? The main news agency. By the way, it wasn't Fox News or CNN. Television didn't even exist. No, AP didn't exist. Good try, though. So let me tell you, New York Times. I'm sure you've all heard of it. So it turned out the New York Times was the center of news in the country. So the New York Times actually decided on the 95% confidence interval and the level to be 95%. Okay. And so that's the most standard. Doesn't mean you always have to use 95%. You can use another percent, and that happens sometimes. So what does it mean to be 95% confident? Okay, what that says, now we can talk about it. So now we're looking at all the different sample means that could happen, and 95% of them should lie in the interval. So we can say is that if many sample means or samples of size, in this case 4, very small sample size, are taken, then each one will produce or result in a different confidence interval. Okay, so if I asked 4 different people in America, I'm probably going to get a different average age of first kiss. Then if I went and asked another 4 different people, I get another different average age of first kiss. So if you look at all the different 4 people you could ask, or many of them, then 95% of the sample means, of the confidence intervals that are produced will actually be successful. Being successful means you actually did contain the population mean. Whereas if you don't contain the population mean, you said, hey, I'm 95% confidence is between 12.2 and 18.8. But maybe it wasn't. So they're all going to result in a different confidence interval. So 95% of these confidence intervals will contain the true population mean age of first kiss. Make that a little bigger because that's important and it's one of the hardest parts of the day. Any questions on this? Okay. By the way, are you always okay on being 95% confident? Are you always okay if there's a 5% chance that you blew it? Okay, you say yes. I hope not yes. Okay, what if blowing it means you're killing someone? Yeah, if blowing it means you're killing someone, I hope you're not okay with 5% chance of killing someone, right? Okay. Okay, and then sometimes you might be okay with 90% chance of getting it right and 10% chance of getting it wrong. Okay, and that can happen too. Okay, so sometimes you're going to have a different confidence level. That's that 95% or 90% or 99%. Okay, and you choose. if you have a confidence level that's 99%, the problem is that the spread, what we call the margin of error, is going to be bigger. Okay, I could be 99.99% confident that the average height of Americans is somewhere between 1 foot tall and 12 feet tall. I know that with 99.999% confidence. But that's worthless because everyone knows that anyway. Do you see that? So the problem with trying to be more confident is that your margin of error is wider. Okay? So if you want the margin of error to be more narrow, then you have to, or one way of doing it is to decrease the confidence level, like to 90%. Any questions on that? Any questions? Okay, so for example, if I wanted to be 90% confident, 0.9, and I hit calculate, then all of a sudden it's between 13 and 18 years old. That's a lot better. Okay. Okay, if maybe I want to be 80% confident, maybe I didn't really care if I'm wrong that much. Okay, then it's almost, 13.8 years old to 17.2 years old. Do you see that? But the problem is that then you have a big chance of just being wrong. So it's a give and take. You can get more confident, but then you have a wider margin of error, or less confident to narrow the margin of error. What if you wanted to be more confident, but not have a big margin of error? What would you have to do? Any thoughts? And there's a great example, by the way, this first kiss example. What would you have to do if you want to be more confident, but not have this big margin, small, big margin of error? Like you want to be 99% confident and you wanted to be within the 1 year of age of first kiss. What would you have to do? Any ideas? The hint is it's right in here. If you can't guess, I'll tell you, you'd have to ask more people. So if you have a small sample size, you're not going to have very reliable data. If you have a very large sample size, then the sigma over root n gets much smaller. So then you get to narrow that margin of error without having to have a low level of confidence. Okay, but the problem of having a big sample size is it takes a lot of work. Okay, if I told you on your project that you had to ask 1,000 people, you probably would have cheated because it would be too much work. Don't you agree? So I did the 31 because that's really the smallest number you can do and still have a normal distribution. So I told you 31 was the number that, the minimum. Okay, but then you're going to have a bigger confidence interval. It turns out wider interval. Any questions on this idea? Okay, so I have a conclusion template, and that is with, I'm going to write XXXX, whatever percent confident, it can be concluded that the population mean, whatever that mean of, in this case, first kiss, is between whatever years they are. So I think it helps to have a template so you can plug into the template and then you won't go wrong. Okay. Okay, and then I also have a template for interpreting the confidence level. And that is if many samples of however many, in this case we had 4, are taken, then each would produce its own confidence interval. And then whatever percent, right, like 95% of these confidence intervals will contain the true population mean of whatever we had. Okay, and in our case, 5% won't contain the population mean. Any questions on that? All right, so just a note, if you have a sample size over 40, then you're okay. You don't have to worry about normality. If you're not, I mean, over 30, if you're not over 30, then you have to assume the distribution is normal, which is usually a very bad thing to do. Okay, so this study of 4 people, you would never do that in any kind of reliable study. Okay, so that was pretty useless. You would need to ask, at least 31 people. And that's why in your project 1, I made sure you did that. Any questions on this idea? All right, so next, let's go over proportions instead. So this average age of first kiss, by the way, the average age of first kiss, like I said, I've been doing this for 27 years. It's gone way up. Okay, when I was a kid, you know what the average age was when I was a kid? No, it wasn't 8. It was more like, it was around 12 or so. It was around 12. Nowadays, it's more like 15. Okay, which we saw our sample mean was around 15. It's actually gone way up. When I was a kid, we had a lot more fun in middle school than kids do now, I'll tell you. Okay, and I learned that through statistics because I always ask this question. And I've watched it, that sample mean has gone up and up and up and up every year. It's kind of interesting. And I've also looked online and I found other people have done the same thing, and they got the same thing I did. It's really changed. And our whole world is changing now, not just for kisses, but sex also, and babies. Is the average age of first baby has also gone way up. And it all goes together. And that's all statistics, by the way. Okay. So now that we've done a population mean, and we talked about sample mean to get a confidence interval for the population mean, now let's do proportions. And what I like to do, and the nice thing is, especially now at this point, I can almost always just pull up a news article, okay, or some article that happened in the last week or so, often in the last day, and I can use it for whatever we're doing in our class, because statistics is that important. Okay, statistics is used everywhere and will help you understand the world. So I was able to find this one just in literally 5 minutes of looking, and it was what percent of Americans right now would find it difficult to pay an unexpected bill of $1,000 right away. Okay. So if you think about the survey question to this, what would you ask? What would you ask the first American you would ask? What are you going to ask that person? And every other American you're going to ask. Let's say you asked, they asked 1,975 people, it turned out. What are you going to ask each of those people? What's the survey question, do you think? Any thoughts? What would the survey question be to be able to answer this question? Okay, how much money do you have saved? You could ask that, but really what they wanted was, it's going to be really obvious when I say it. Would you find it difficult to pay an unexpected bill of $1,000 right away? And let's see you pop in the chat box whether you would find it difficult to pay an unexpected bill of $1,000 right away. Pop your answer. Okay. Okay, and you'll notice we have answers no, and we have answers yes, which means this is not a quantitative data. Okay, this is the yes or no question, and that's really important. Okay, if you get that wrong, you're just going to fall apart. So the very first thing you should do, and pretty much everything we do for the rest of the class, is look at that survey question and say, is this a yes/no question? Or is it quantitative that has a number answer? And this is yes/no question. Okay. So this is a yes/no question. And what they found, this is from the Quinnipiac University Poll. They do a lot of surveys, so they're a good one to use. And they sampled 1,975 people. And by the way, they used a variation of stratified sampling. Again, I'm not going to go through the whole article for you, but you can trust me in that. You can read it too. I have that link. But either way, you can just look it up too. You can find it. Remember this P hat, P with a hat on top? That is the sample proportion of yes answers. That's what that P with the hat on top. And I do want to let you give you a heads up. I don't expect any of you to type in P hat into your discussion post assignment if you're doing something about proportions, because it's actually really difficult to learn how to type in P hat and make it work. So just because I did it doesn't mean you're expected to know how to do it. You can use PHAT, and that's fine. I'll be happy with that, just because it's actually pretty hard to do with the equation editor. Okay, but they got 0.2. Wait a minute, they didn't get 0.26. They got 0.56. That was a typo. I actually did this just a couple hours ago, so I remembered my number, and it was a typo. And they got 0.56. All right, so how do you find out the number of yes answers? This is not that hard. How many people said yes? How do we decide? No. How many people said yes in this Quinnipiac poll out of the 1,975 people surveyed? Wasn't two, by the way. A whole lot of people said yes. Okay, if you don't remember, you take 1975 and you multiply that by 0.56. And I can do that in my calculator. And it was 1,106. Any questions on that? Okay, and if I want to find out how many people said no, there's two ways. One is I can take the 1975 and just subtract the number said yes, and that'll be the number said no. So 1975 minus 1106 is 869. Okay. Again, I don't expect you to necessarily do this in your head. You can use a calculator anytime. You could also multiply 1975 by 1 minus 0.56, and you'll get 869. Any questions so far? Okay, what we want to do is we want to find out a confidence interval, maybe a 95% confidence interval. So I can't use this one. Okay, because this is all about with data, it's for a mean, that's not what we want. So I can go back to the calculator menu. Let's see if you can tell me what calculator number I need to click on. Hope is I tried to make it easy, so you should be able to just read it and know which one. So what calculator should I use? Which one is best to use? Okay, so number 9 is a confidence interval for a mean. But a mean is when you have quantitative data, right? Numbers for the survey question. So it's not number 9. One more guess, because it's very important that you know which calculator. Number 10 is also for a mean. Do you see the word mean? Right, number 10 is the one we just used. for the average age of first kiss. Which one? Don't see jumping in. Okay, it's a proportion. That's not binomial, it's confidence interval for a proportion. We want a confidence interval and we have a proportion, we don't have a mean. So I click on confidence interval for a proportion. And it asks for N, which was 1975. It asks for X, okay? And X is what they call the number of successes, okay? Which is standard in statistics. I don't like those words because sometimes it's a bad thing. Sometimes it's a good thing, but it's the number of yes answers. And remember, the number of yes answers was 1106. So 1106. Confidence level, let's do 95%. And hit calculate. And there's our confidence interval. And this is way more decimals than I care about. How about 3 decimal places point? So 53.8% to 58.2%. So 53.8 to, again, 58.2. Okay, and by the way, it reminds you what the p-hat was. And there's our confidence interval. Any questions on using the calculator? Okay, let's interpret it. And that is with 95% confidence. Between 53.8% and 58.2%. Whoops, percent of all Americans. Okay, and I want to note that I want to highlight all. You in this class, by the way, if you don't state specifically that you're referring to the entire population, so this is all Americans, and the last one, by the way, I wrote population mean. Okay, so you have to specifically refer to the population. And then what was this about? Would find it difficult to pay an unexpected bill of $1,000 right away. So I can just copy and paste that in. So with 95% confidence between 53.8% and 58.2% of all Americans would find it difficult to pay an unexpected bill of $1,000 right away. Any questions? Any questions on getting this confidence interval and interpreting the confidence interval? Okay, for the confidence level, I'm just going to say it, but I'm not going to spend a lot of time on it. I'm not even going to type it out. But for the confidence level, it's the same idea, is that if you were to survey many groups of 1,975 Americans, then each group would end up resulting in a different confidence interval for the population proportion of all Americans who find it difficult to pay an unexpected bill of $1,000 right away. And 95% of these confidence intervals would contain the true population proportion. of all Americans who would find it difficult to pay an unexpected bill of $1,000 right away. So it's the same idea as what we just did, just a different context. Any questions? Any questions on this? All right, so now I want to look at sample size for a mean. Okay, so now we've kind of talked about confidence intervals, very important. Let's talk about how big a sample size you need to have a confidence interval that you're satisfied with. So just a reminder, the central limit theorem tells you sigma sub x bar is sigma over root n. I did some math and I get n equals z sigma over e quantity squared. Okay, you don't always have to do that math, but I just want to let you know that with some algebra, you can get there. But what I did, which actually made some people not very happy, I made it too easy. But my students are never unhappy about that. But there's some other faculty and some other colleges that weren't happy that I made it too easy. But hopefully you'll be okay. So let me do an example. All right, suppose you want to find a 95% confidence interval for the population mean hourly wage of nurses in California. Okay. Based on a preliminary study. So maybe you surveyed 15 nurses or something, okay, which isn't enough, but you could get the standard deviation of them and at least you get a good guess of the standard deviation. So based on a preliminary study, the standard deviation is assumed to be $25 an hour. If you want a margin of error of being no more than 50 cents, so that means you're not off by 50 cents on either side from the sample mean, basically. How many nurses must you survey? So it's really, really important to be able to come up with how big a sample size you need. Because if you don't do that, you won't even know what to do. If you want to do a study, how many people should you study? And this is how you go and do it. Any questions so far? Okay. And I'll tell you, you might guess, if you think about it, there's, how many nurses do you think there are in California? There's a lot of nurses, right? Maybe 1 million or so nurses, something like that. Probably not 1 million, but maybe 200,000 nurses. Remember, we have a big state with like over 40,000 people, 40 million people. Okay, so do you have to like survey half of them? That would be miserable because you have to survey like 100,000 nurses. Good luck. So you want to like decide how big a sample do you need to actually have a nice confidence interval with a small enough margin of error. Any questions on the idea? All right, so what I'm going to do is I'm going to go back to the calculator menu. What calculator do you think I need to do? Which calculator number do you think we're doing? So what number do you think is the right one for this? See if you can get it. Okay, number 9 is when you want to find a confidence interval, but we don't need the whole confidence interval. What we want is a sample size. And the survey question will be what, you're going to ask this nurse, how much do you make an hour? So it's going to be sample size for a mean because the nurse isn't going to say yes. The nurse is going to say, I make, $85 an hour or whatever. So it's sample size for a mean. Any questions on that? Okay, so it's important that you can kind of come up with the right calculator number. Okay, and it asks you, what is sigma? What's your population standard deviation estimate? And that's 25. what is E? E is for error. And the margin of error, we want no more than 0.5, 50 cents. And the confidence level, we want a 95% confidence interval. So that's our confidence level is 0.95. Any questions on that? And hey, calculate. Okay, so you would need a big survey, by the way. You would have to sample 9,604 nurses. Okay, which is a lot. So survey 9064, 9,600, 9604, sorry. 9,604 nurses. Any questions at all on coming up with this? Okay. By the way, you may not need it to be within 50 cents an hour because most people don't care about that small amount of money. Some people do, but maybe $2 an hour, and we can see how that would change things. So if it was $2 an hour instead, then you'd only have to survey 601. That's a lot less. So there's a big difference if you increase the margin of error. If you're okay with an increased margin of error, you don't have to do as many for surveying. Any questions on that? All right, so then the last little piece is, what about if you want to find a confidence interval instead of a mean, how about for a proportion? Okay. So I have some examples. So let's suppose that you want to find a 99% confidence interval for the population proportion of cars in the United States that are electric vehicles. Okay. And let's suppose you want the margin of error to be no more than 3%. How many cars must you look at? Okay. So I'm going to go back to the calculator menu. And let's see if you can tell me what calculator number to use. Which one's the right one? And again, I want to find out how many cars must you survey to find a good confidence interval for EV cars. Yeah, this is going to be number 13. It's sample size for a proportion, because it's yes or no. Is that car an electric vehicle? Yes or no. Do you see that? And we want a sample size because it's a how many question. All right, so it says, do we have an estimate for P or do we not have an estimate for P? So here for part A, nowhere in here do we have any idea on what the proportion is. So we don't. So click no, no estimate for P. I want the margin of error to be 3%. So 0.03, because that's how that percent is. And then the confidence, I want to be 99% confident. So 0.99, and I calculate it. And it's 1,844. So look at 1,844 cars. Any questions on part A? Just a note, if we wanted a 95% instead of a 99%, do you think we'd have to survey more people, more cars, or look at more cars or fewer cars? If we were okay with a 95% confidence instead of 99. More cars or fewer cars? What do you think? We'll find out in a second. Any guess? Can't hurt to guess, by the way. Let's see, y'all jumping in. So if we wanted 95% instead of 99, and hit calculate N, instead of over 1,800, it's just a little over 1,000. It's fewer cars. So the idea is if you want to be more confident, it takes more work. You have to look at more. Whereas if you're okay being less confident, like 95%, then it takes less work. Not as big a sample size. Any questions on this idea? All right, now let's answer the last question. Let's suppose you looked at last year's data and 2.2% of all cars were EV. How many cars would you need to look at for the 99% confidence interval? Okay, so we still need a 99%. What's the difference now? Remember, with 99%, it was 1,844. But what's the difference for part B? Let me remind you on part B. How has part B changed? We still want a 99% confidence interval. We still want a 3% margin of error. But what's different? Yeah, we have an estimate. We have an estimate for P. And our estimate for P is 2.2% or 0.022. So I'm going to click Have Estimate for P. Now it asks you, what is that estimate? And it's 0.022. Any questions on that? And now if I calculate N, you're going to see a big change. Instead of like over 1,800 cars to look at, it's not very many. It's now 159 cars. Big difference. If the estimate is far from 0.5, you're going to see a big difference. Just to let you know. Any questions on getting this 159? So now we only need to look at 159 cars, much fewer than when we didn't have an estimate. So having an estimate is a good thing, by the way. It's a lot less work. So it's always a good idea to like do a little bit of a survey, use that as an estimate sometimes, and then sometimes you have a lot less work to do in terms of the sample size. Any questions at all on this example? Okay. Today, as I promised, is a little lighter, not quite as much material. We don't have to talk about a project. I will let you know that project 2, one big part of project 2, any guess, is going to be to find any guess after seeing today's webinar? Yeah, confidence interval. Okay, but we're not quite ready for it because it turns out project 2 is really focused on the information that you have up to chapter 10. And it's going to be confidence interval for a difference between means, which we haven't talked about yet. So I'm not ready to get into any details on project 2, other than just kind of give you a warm up of there's going to be confidence intervals involved, but more advanced than what we did today. So what I have, again, today was a little bit shorter than usual, but it's still not too short. We have our secret word. And the secret word is population, because you must refer to the population when you are talking about or interpreting the confidence interval. It's the population mean is between these numbers, or the proportion of all people is between these percents, or the population proportion is between the percents. So the word population is kind of an important word for this week. Okay, and that is pretty much everything I needed to say for confidence intervals. And let you know again, there's an exam this week, so be ready for that. So I'm going to stop the recording.